Hello, stats students. Today we're going to start section 11.1 in chapter 11. We're going to start looking at chi-squared goodness of fit tests. So in 11.1 we'll focus on goodness of fit tests, and in 11.2 we're going to look at other types of chi-squared tests. So in previous chapters we looked at inference for comparing proportions of successes for two populations. But sometimes we want to examine the distribution of a single categorical variable in a population, and that's when we use the chi-square goodness of fit test. So basically we can decide, and then later in this chapter we'll look at deciding whether the distribution of a categorical variable differs for two or more populations. That's going to be a chi-squared test for homogeneity. And that's when we don't have a distribution in mind ahead of time, but we're comparing two groups to each other. And then there's another type of chi-squared test we'll look at to look at the relationship between two categorical variables, and that's called a chi-squared test for association independence. In 11.1, we're going to focus on the chi-squared goodness of fit test. So yesterday you did the Candyman activity. So we had a distribution in mind. The Mars company says that here's what percent they put in their M&M bags for each of the 6 colors. So then I had you open a fake bag of M&Ms, and basically you might get something like this. So these purplish colored bars are the actual numbers of observed counts for each color, and then these red bars are what I would expect. So you can see that I had, in this bag, I had much more yellow candies than I would expect, and much fewer blue candies than I would expect. You then did some calculations to get a chi-squared value for your bag of M&Ms, and here is what everyone's chi-squared values looked like. So you can see the lowest was around 2.3. There were a few, several, I guess, in the 2s, some around 5, one around 8.3, and then there was one very large value of 15 point something. That bag of M&Ms had, like, I don't remember what color it was, but like maybe much more yellows than expected. So overall, their bag of M&Ms was really far away from those percentages that the Mars companies said. So you can see, on average, we were at about 5.3. That is with the outlier factored in. So most of us, if we think about these being like reasonably small values, most of us, we would say that our bags weren't probably that far away from what the Mars company says. However, there was one of us that we might say that's an unreasonably large number, which means that the Mars company's claim, maybe for that person, if we just looked at that person's bag of M&Ms, we would have reason to question the Mars company's claim. Now, we only did 12 samples, though. Had we done a lot more, we would start to see more of what the shape would look like if you open many, many bags of M&Ms. You can see that, yeah, we got some outliers there, a big cluster on the left. And if I did 500 bags of M&Ms, so I simulated opening 500 bags of M&Ms, we start to see the skew right shape. However, there's my pup. He sees somebody outside. I'm going to keep going. But then I did a lot more samples, and you can see that shape starts to smooth out a bit. And so here's simulating 3,000 bags of M&Ms being opened, and you can see this skew right shape. And then I drew a curve through those bars to see this kind of general shape here is what we get when we do this many, many times. So here is, let's say, a bag of M&Ms that I opened, how many of each color I observed. You can see that I had a total of 60 M&Ms in my bag. Let's say that I wanted to just look at the blue M&Ms. So in my sample, I had, my p-hat for blue is 9 out of 60, or 15% blue. The company's claim is that 24% of M&Ms should be blue. Now, that's not too close to what I observed. So what I could do is I could run a one sample z-test for proportion like we learned in chapter 9 just to compare the blue M&Ms I got to the percent of blue M&Ms that they claim. And here would be my hypotheses. The null hypothesis is that p is 0.24. The alternative is that p is not 0.24. And then I could run a significance test to see whether or not this gives me evidence to reject the null hypothesis and conclude the alternative. I could then do that same type of test for orange, and then another test for green, and then another test for yellow, and so on and so on. And I could do 6 different one sample z-tests, one for each color. Now, there's a problem with that, and that is performing that many tests for a proportion would be pretty inefficient. You'd have to do 6 different tests, and that does lead to the problem of multiple comparisons. Remember, if you do many tests, you would expect to get some type 1 errors, and too many, in fact. So we're going to look at a different way to consider all of the colors at the same time instead of doing each color individually. And that method is called a chi-squared goodness of fit test. So that's what we're going to be looking at in 11.1. We take into consideration all the colors at one time. So here's what the null hypothesis can look like for a chi-squared test. You'll notice I've got a sentence here. It's basically that it's a claim about the distribution of a single categorical variable. So in this example, it's that the company's stated color distribution for M&M milk chocolate candies is correct. And you can see I can write the null hypothesis that way with a sentence. The alternative is that that categorical variable does not have the specified distribution. So it would be the company's stated color distribution for M&M candies is not correct. So that's one way you can write the null hypothesis and alternative hypothesis. Another way you could write it is using symbols. You could actually list the stated proportions for each color. So our null hypothesis could also be written this way. The alternative hypothesis, however, you have to be careful if you're doing it this way. It would not be like each one of these with a not equal sign, because for the alternative, some of these could be correct, but it's just that any one of them is incorrect. So that's how we write it. So it's at least one of these p's is incorrect, because for the alternative, for this to be wrong, for the null hypothesis to be wrong, it could have like 4 of these 6 as actually matching up, but 2 of them maybe are wrong. And then that's not the null hypothesis. So the alternative is that at least one of them is incorrect. And then if you write it this way, you have to define the parameter that you use. So I have to define p sub color, and instead of defining it 6 different times, I can just write it like this. It's the true proportion, population proportion for that color. So the idea then of the chi-square goodness of fit test is that we compare the observed counts of our sample to the counts we would expect if that null hypothesis is true. Now, the more the observed counts differ from the expected counts, that's more evidence against the null hypothesis. So in general, the expected counts can be obtained from multiplying the proportion of the population distribution in each category by the sample size, and that's what you should have done yesterday in your activity. Now in my bag, since this sample size is 60, I could just take, for example, if Mars says 24% of them should be blue, I can just do 24% of 60, so my expected count is 14.4. And then I can do that for each color. So I use that same method for each color. 20% should be orange times the sample size, 16% should be green times the sample size, and so on to get all my expected counts. And then I make a table of my observed counts and my expected counts, just like you did in your activity yesterday. Next, I would then see if this data gives convincing evidence by comparing the observed and expected counts. So the farther away they are, the more evidence that is, that the null hypothesis is not true. So you can see blue, I'm pretty far away. Yellow, I'm also pretty far away. Those are probably my 2 biggest differences. So we see some fairly large differences, but how likely is it that differences this large would appear just because we took a random sample of 60. We don't expect to get exactly the same number as expected, but like how likely is it to get differences this large? Well, the way we do that is we calculate our chi-squared statistic. And here's the formula for that chi-squared statistic. And this is what you calculated yesterday. You did all the observed minus expected, you squared them, you divided by the expected, and then you added them all together. So for my bag of M&Ms, it would look something like this. For my first color, I observed 9 minus the expected was 14.4. I square that difference, then I divide by the expected. Then I do that for my next color, and so on and so on and so on. And my chi-squared value was 10.18. So then we have to think about like, okay, 10.18 is that, oh, sorry, here that is again. Here's that 10.18 again, but you can see now here are my, 6 different colors, and here's the fraction for each color. Add them all up, there's that 10.18. So this chi-squared value, you can think of it as a measure of the distance of the observed from the expected counts. Like that's the, distance of all 6 combined. Now, larger values for chi-squared are strong evidence against the null hypothesis, because that would mean the observed counts are far from what we would expect if the null hypothesis were true. Small values for chi-squared, suggest that the data is actually consistent with the null hypothesis. Basically, it's not. Smaller numbers are not surprising if the null hypothesis is true. But then we have to think about, okay, what numbers count as large? And the way you do that is you look at what would happen if you did this many, many times if the null hypothesis were true. And you can see this is what the distribution of those chi-squared statistics looks like. 10.18 is about right here. So how often do we observe a value that large just because of randomness? Well, I don't know. You'd have to find the proportion that are to the right of that. And I don't know what that is. One thing to understand is that this statistic is not a normal distribution. This is a right-skewed distribution, and you can only have positive values. So chi-squared can never be negative. When the expected counts are all at least 5, that's one of the conditions. The sampling distribution of the chi-squared statistic is close to a chi-squared distribution. This is a new distribution. We have the normal distribution, we have the t-distributions, and now we have chi-squared distributions. These also, though, have a degrees of freedom. The degrees of freedom for a chi-squared distribution are equal to the number of categories minus 1. So in our case, the number of categories was 6 because there were 6 colors, so there would be 6 minus 1 degrees of freedom, or 5 degrees of freedom. So here's what different chi-squared distributions look like with different degrees of freedom. So there's degrees of freedom 1 and 4 and 8. So how rare is this 10.18? Well, you can use a table to look it up. Table C, go to degrees of freedom 5. I'm looking for 10.18. It's between these two values, so I know my p-value, or area to the right, will be between these two numbers. And of course, then you can use your calculator instead. Distribution, option 8 is a chi-squared CDF. My lower bound is 10.18. My upper bound is a very large number. My degrees of freedom was 6 minus 1, which is 5. And then my calculator can give me a much better answer than this table can. It tells me the p-value is 0.07. So the p-value for this test based on our sample, according to the table, is between these two numbers. My calculator can give me a little better answer of a 0.07 or so. So with that result in mind, since our p-value is greater than 0.05, we fail to reject the null hypothesis. That means that this bag of M&Ms doesn't give us sufficient evidence to conclude that the company's claim distribution is incorrect. However, one thing to consider, I'm not going to read all of this, but is basically that the conditions might not have actually been met, though. because of the way factories bag the M&Ms, it might not actually be random because on one day they might be making more of one color than another. So basically when you're doing these, their conditions matter a lot. So that's it for today. We'll continue talking about these tests tomorrow.